Hello and welcome back to Compiler Programming. I was debating with myself for a while how I want to make this video or if I want to make it at all, because this is in the end going to be a very boring refactoring. So I decided to skip the actual code and instead talk about what I want to do and why. And as you probably know from the title of the video, we are going to be talking about numbers, in particular about number literals. So why are they hard to deal with? Well, when you have something like 1 or 100, it is pretty straightforward what that means. When you parse the program, you understand that it's a number, and if this was a high-level language or interpreted language like Python or JavaScript, we would just choose the biggest number type for this. So for example, in JavaScript, all numbers just are doubles, which means they can be integers of up to 53 bits of value, or it's a double, so it can also hold floating point numbers. This is pretty convenient, but if you want to do more low-level programming, you want to control more precisely what is the size of the type, right? So in this particular case, we want the size of this I to be 8 bits and we want it to be signed. Funnily enough, here we first of all probably want unsigned, but even more so, we don't really care what is the type because we are going from 0 to 100 and it's never going to get to a point where we actually do care about the type. And this is where the trickiness starts to come in, right? So if I have this 100 as we discussed, what type is it by default? So if I just do say x is 1, 2, 3, and this is the syntax for introducing a new variable and inferring the type from the right-hand side. This is kind of an interesting choice. I actually tweeted about this, how different languages deal with it in my Twitter, so if you are not subscribed, please do. Sometimes I post just interesting links and information about programming languages and such. But what I did here is I went through the list of programming languages that you see here and started to figure out how they decide what type should the literal number be. And it is kind of interesting. So a lot of newer languages such as Go, Zig, Odin, and Haskell to a certain extent, they just implement arbitrary precision integers or big int types, which means that you can, as long as you do any kind of operations at compile time, so if you do something like this with a very long number, it will be perfectly fine in those languages. Now, realistically, this kind of multiplication is only required for sort of specific types of applications. I can imagine scientific applications, or I don't know, maybe something with simulations or stuff like this, which probably also can be considered scientific. But what I'm trying to say is like that's not very common. I mean, you also maybe something in cryptography where this is relevant, but for general purpose, like in my career of, I don't know, almost 20 years now, I have never actually needed this kind of stuff. And obviously, your experience may vary, and it may be that you actually do need this, but what I'm trying to say is it's not very common. And if it's not very common, I'm not sure that's a good idea to have it as default in the system. Additionally, the reason I don't like arbitrary precision stuff is because if you have something like this that is happening at compilation time, but at runtime, you don't by default implement numbers as big ints, you will have this weird mental mismatch, right? Okay, here I can use these kind of numbers, here I can't use this kind of numbers, here it will do like all these kinds of weird conversions. So I, in general, ended up thinking that I don't think that big ints are a good idea at compile time if they're not default at runtime, and I cannot make them default at runtime because I want this to be a low-level language. Now, of course, I would want to support big int eventually as one of the types, so if you do need to have this kind of computations, obviously that should be possible. It should be a library that provides a big int support. It might be the library that is shipped together with a compiler, so the standard library, but I don't think that should be something that is there by default. Okay, so that's about big integer or arbitrary precision stuff. Next, there is also an interesting column here that's called n-bit choice, and this has to do with what I told you before of how it is decided what type is this 1, 2, 3. In C, you always have to specify the type on the right hand side. So in C you would have, I don't know, U8, Y is 1, 2, 3, and then the compiler starts sort of from the left side. It figures out that Y is of type U8, and it says that this is a 1, 2, 3. But if we use it in an expression, and so imagine that we have some kind of a call to foo and it's 1, 2, 3, then this is very interesting, right? What type is it? Again, in C, it is pretty straightforward because there is no function overloading, and by the rules of the language, I believe that these will always be promoted to an integer and then used for matching. And the same thing probably in C++. Now, the question is, what do you do if you want it to be a larger type? Well, you can do this kind of stuff. So you can do LL and or just L, which means long. LL is long, long, and LLU is long, long, or unsigned long, long. And if you want to be explicitly unsigned, you just do U. Why would you need this? Well, you need this if you have something like this. FFF, FFF, right? So if I don't write this, then this is an integer, and it's sort of a negative integer because we are at F. If it's U, then it is now an unsigned integer. So in languages such as C, Java, C#, Rust, and Nim, they all sort of opt in to allow you add these kind of, let me actually zoom a bit, add these kind of suffixes to the number to specify what is the size and whether it is a signed or it is an unsigned number. This is how they deal with it. Okay. Again, newer languages, usually they just allow you to do this kind of stuff, and even in cases of foo, and then they just check by the sort of required number of bits of the value if it will fit into specific range or not. And these languages just deal like this with it. Now, Go and Zeek don't really have function overloading, so that's a bit of a non-concern for them in a sense, and Haskell as well. Odin has limited overloading, and Jai I can't really play much with it, but from what I can tell, it has some rules about casting, and I think it will still consider it a a 64 number by default. So what I did, so the way it works right now in mass, and we can actually take a look at number literal type. Let me search for this. Yes. The way it works is I have this very special struct that stores whether the number was parsed as binary, decimal, or hex number, and then it stores whether it was negative number, and it stores the actual bits of this number. And then whenever we need to actually convert it to a specific number, we do the check. I think that is the correct one. To find it. So, yes. So if we convert a number literal to a number, we do this call to value number literal cast, which is probably in here. Yes. And it does the check for the ranges. So it checks that the literal that we're trying to cast, it can actually fit into the right size. This protects us from things like x u8 is minus 1, 2, 3. So that is a no-go because this is a negative number and we can't fit it. Or if it is larger than 256, it will also not fit. So this will be explicitly disallowed. This is the check that's happening in here. And it is sort of working, but at the same time, it doesn't feel very consistent. I also don't like how the negative positive stuff is handled. It's sort of awkward. This number is this very special type that you can't do bit operations because they're in a sense undefined. Again, if I show you here, like I store the negative bit as a separate one, so the whole 2's complement arithmetic doesn't make sense for this. It's just it breaks all kinds of assumptions about how numbers work for a systems programming language. So I'm not a big huge fan, but I didn't really know how I want it to work. Yeah, in a sense, this is why I was doing this stuff. Now there is also floating point stuff, but this is much simpler because there are only basically two types really that are in real use, either single precision or double precision, and it is more or less straightforward to just say, okay, I always parse numbers as double precisions, and if they're constant, I just allow you to assign them to single precision ones. If they're non-constant, then you cannot do that. And that seems to be a pretty decent rule, so I'm not particularly worried about the floating point stuff, and it is more or less consistent how it's done. Okay, so getting back to integers, what am I going to do about them? The plan that I have right now is to introduce a new type, and as you might have noticed, I also have this WebAssembly open in the extra tab. Why I have this? So in WebAssembly, you actually only have these kind of number types. You don't have bytes, you don't have 16-bit integers, you only have 32-bit or 64-bit integers and single or double precision floating point numbers. And what I will do, as you can probably see from here, is I will even drop 32-bit for the compile time stuff. So I will only have 64-bit and floating point double precision numbers, so 64-bit floating numbers. And then in the same way as with the with WebAssembly, they are not signed or unsigned. They're just defined to be, for integers, they're defined to be 2's complement. And then you choose whether to treat them as signed or unsigned by choosing the operation. So there's going to be a signed multiply and unsigned multiply, signed and unsigned divide. And for addition and subtraction, you don't need different types, because that's one of the cool things about 2's complement, and I encourage you to look into that if you're not aware. But the whole idea is that you can use the same logic for signed and unsigned numbers when you do in addition, and subtraction is addition with a negative number, so that's the same operation. So yeah, that is basically the plan. Now there is still a question of what is going to happen when you do the stuff that we talked about, right? So if I do x is 42, well, in this case, it will actually just keep being this type of I64. So it will not convert to signed number. It will just stay I64, because honestly, in a lot of cases, when you're dealing with data, you don't actually care if the type is signed or unsigned. You mostly care about the size of it. So I think that is good. I might even introduce I32, I8, and I16 types in runtime as well. It's sort of not sign with sign unknown counterparts, and just deal with it. Now, one thing that might be annoying, and something that I was thinking about how to do, is ideally you would like to be able to do something like this. But as I told you, when you don't specify the signedness of the number at definition side, so it will be at this I64, I need to decide which kind of multiplication will I do here. Is it going to be a signed multiplication, or is it going to be unsigned multiplication? And what I figured out just recently, and I realized that I could sort of avoid this choice if I know that both numbers are positive, or more like this, if the first bit of the number that is distinguishing whether it is positive or negative is not set, right? Because in those cases, both division and multiplication actually end up in exactly the same value regardless of the assignment, so this will work. And then what if you do need the negative number? Well, here's the trick. When you do minus on this, at this point, this number will actually be turned from an I64 to an S64, or a signed integer. Because you explicitly said, yeah, I want it to be signed because I'm saying this is a minus 42, right? I care about the sign. And then this operation is also very well defined. This is now a signed number, and everything is great. I'm still thinking whether I always should default for it to be a signed number or not when I'm doing this type inference. It's a bit unclear, to be honest, what is going to be more convenient or less convenient. But honestly, I think for a lot of cases, just keeping it straight up as 2's complement number and keeping this logic is going to be perfectly enough, unless you start to do this kind of operations, at which point it would be actually good if compiler yells at you and asks you, what do you actually mean here? Do you mean this to be signed, or do you mean this to be unsigned? And then you can go back in here and specify, okay, I want this to be actually unsigned 64-bit, and this goes. And of course, when you want to assign it to a smaller number, so say I want it to be assigned to U16, Actually, U8 will also work in this case. Because this is non-compile time, I can have a special rule that says, oh, okay, we have this value known at compile time, so this would be 126, right? If I can do my math correctly. And 126 is perfectly assignable to S8. It is even assignable to S8 and to U8, doesn't matter. So this is a perfectly valid assignment when you just know that this type is statically known. So yeah, that is basically the plan. I think this should turn out okay. Maybe after I'm finished with it, I will be like, oh no, this is completely horrible and I have to roll it back. But I still thought I would record a video and explain what are my thoughts about it, and maybe I would have some interesting thoughts of your own. Please leave them in the comment. I would be super happy to hear what you have to say. And yeah, I guess that's all for now. I will be back with some coding, hopefully pretty soon. But for now, thank you very much for watching and see you next time.